Oh, okay.
I haven't gone back and checked how often.
Be tough in California. Okay, let's start. So our speaker this morning is James Sparks from the University of Oxford, and he's talking about gravity duals of Susy gauge theories on curved manifolds.
Thank you very much. I'd like to thank the organisers for inviting me to this wonderful workshop that's going on. And I will be continuing the theme today of localization. We've had several talks over the past 2 weeks on localization in supersymmetric gauge theories in different dimensions. And today I'll tell you about something a bit different, which is the gravity duals to this. Yeah, I should say this is work in collaboration with Dario Martelli and Dario's student, Achilles Passius. Okay, so I will start with a fact, which is that you may put Euclidean supersymmetric gauge theories on compact curved manifolds. Okay, so for example, Daniel Jaffris talked about the three-sphere, the round three-sphere, and defining n equals 2 supersymmetric gauge theories on the round three-sphere. We had a talk last week on supersymmetric Yang-Mills in 5 dimensions on the round 5-sphere. In my talk, I'll talk about these cases where the background metric is not round. So it's a non-trivial curved manifold. And when you do that, you also have to turn on a background gauge field. So plus background gauged R symmetry. Okay, so these will be supersymmetric gauge theories I'll be considering, for which you can have an R symmetry, that is the fermions are charged, the killing spinors are charged under a U1 R symmetry, and I turn on a background gauge field for that. That's important in order to find supersymmetric gauge theories in this case. Never quite sure which order to use the boards with these things. Anyway. All right, so I mean, in principle, you can do this in different dimensions, but I will focus on dimension 3 because that's the only case where there are published results on this. So I'll focus on EG. Sorry.
Why Euclidean here is relevant? So
Sorry?
What difference it makes that these are Euclidean gauge theories? So why are you working in Euclidean signature and not Lorentzian?
Well, this is important for the localization. I mean, well, you normally work in, well, it depends what you mean by normally, but you often work in Euclidean signature when you're defining path integrals, partition functions, and so on. Yeah. I think that will do as an answer for now. All right, so I'm going to focus on three-dimensional, n equals 2. So there'll be Yang-Mills, shown Simon's matter. Theories. And it will be on squashed 3-sphere.
Sorry if I can just interrupt. About that previous question, isn't it also harder to have Minkowski signature on compact manifolds?
Yeah, sure.
They're not
Yeah, of course you would have closed time-like curves in that case, sure. Yeah. Okay, so these are n equals 2 theories in 3 dimensions. So in the vector sector, gauge field sector, this will be an n equals 2 vector multiplet. And so I'll remind you that includes a gauge field A, mu, and a scalar sigma plus fermions. And in fact, this gauge field, this scalar sigma will play an important role. And the matter will be so the analog of of a chiral multiplet in 4 dimensions. So this is a chiral matter field, so it'll have some complex scalar and some fermions in it. So these are the sorts of theories I'll be talking about. And so these squashed spheres, in fact, there are a number of models sort of on the market in the literature. There are 3. So I'll write them down, what they look like. So the first one is it's often called the Berger sphere by mathematicians. And the metric looks like this. So it's a metric on S3. That's a metric on S2. Theta and phi are the usual coordinates on S2. And I view S3 as a hop vibration over S2. So this is a connection on the hop fiber of S3 viewed as a vibration over S2. And V here is a parameter. It will be the squashing parameter. The round metric is V equals 1. And then I'll also need to turn on a background gauge field. And in fact, there are 2 choices. So one, okay, so this is A3 because it's a 3-dimensional gauge field. I'll be talking about the gravity dual a little bit later, where there'll be a 4-dimensional gauge field. And this is case 1. Okay, so there are 2 choices. That way around, yeah. Okay, so the gauge field is just proportional to this hop connection, the connection on the hop fiber, with this funny dependence on the squashing parameter V. And so this particular model was studied by Hammer, Osamichi, and Lee 1 year ago, February last year, February 2011. So that's this background gauged R-symmetry. There's another choice, though, for this gauge field, which was considered a bit later, A2, in September last year. And it looks rather similar, 1 over 2v squared. It's just there's a square root here. Otherwise, it's the same. And this was Imamura Yokoyama in September. Okay, so I'll tell you why, what the difference is between these 2 in a moment, okay? And the other model, which is perhaps more famous, is the sort of elliptically squashed, let me call it an ellipse, elliptically squashed S3. And that has a more complicated metric. It's in a rather different coordinate system. So I'll write out the metric. Actually, I don't remember which way around they are. Cos squared theta d phi 1 squared. So this is a different sort of coordinate system on S3. So d by d phi 1 and d by d phi 2 so if you imagine if you view S3 as embedded in R4, R4 is R2 plus R2, and these 2 killing vectors rotate the 2 copies of R2. Different coordinate system. Okay, so and then you have this squashing parameter B, and the gauge field A3 is, there's a square root again, slightly complicated thing, d phi 1 minus 1 over b squared d phi 2. Okay, good. So these are these squash spheres that are around in the literature. And so the statement is you can define a generic n equals 2 supersymmetric Yang-Mills-Chern-Simons matter theory on these spaces. Okay, yeah, I should perhaps say you recover the round sphere by taking the squashing parameters to 1. So the squashing parameters are B and V, or V and B. So there's a B here, and there's a V in the other example. And the round sphere is, in each case, the limit where you take the squashing parameters to 1. Okay, so if you put B equals 1, this is a round sphere. If I put V equals 1, this is a round sphere. And moreover, in that limit, the gauge field is 0. Actually, it's pure gauge in this particular case. Gauge equivalent to 0. Okay. So they're both one-parameter families of deformations of the round sphere.
Sorry, can I just ask, is there some reason why it should be 0 in the limit of round spheres, or just is for these choices? I mean, could you not have a round sphere theory with a gauge field? Or?
Actually, you can, yes. So I'll comment on that towards the end, actually. But yes.
So here it just happens to be a property of your.
Yeah. So I mean, okay. Yeah, I'm going to make so far in the literature these are rather ad hoc constructions. I mean, you do it and it works. But I'll comment more on that in a moment, actually. So let me say a little bit about how you define these supersymmetric theories. So just a rough idea. I'm obviously not going to start writing out Lagrangians and supersymmetry transformations for these things. I'll be here all day. But the idea is you appropriately deform the flat space, Lagrangian and supersymmetry transformations. And well, other people have talked about this for the case of the round sphere, in round 3 sphere, round 5 sphere, and so on. So people have already talked about some of this in a bit more detail. It's very similar for these cases. It's just there's an extra squashing parameter. It's a little bit more complicated. But for example, if you have some covariant derivative in flat space, like this is d mu, this is some charge q, this is a dynamical gauge field a mu. The first thing you want to do is covariantize the d mu on the background. This is usually the covariant derivative with respect to the metric. The gauge field term will stay the same, but you've gauged the R symmetry. So there's also a term with this background gauge field, and delta here is the R charge of whatever field this covariant derivative is coupling to. There's an unfortunate convention that R charges are called delta in 3 dimensions. It looks like conformal dimension. That's because people have in mind conformal field theories, superconformal field theories, for which the R charge is equal to the conformal dimension. These are not necessarily conformal field theories, but actually for my talk they will be. Anyway. All right, so that's the first sort of deformation that you do. The other important thing is that these backgrounds admit killing spinors. Backgrounds admit charged killing spinors. So in flat space you would just have constant spinors. D mu epsilon is 0, epsilon is your spinor. That gets replaced by a killing spinor equation, so there'd be the spin connection, d mu acting on the spinor. It's charged under this R symmetry gauge field with charge 1, so you'd normally call that a spin C spinor. It's charged under a gauge field, and then that's equal to something or other. I'll just write dot dot dot. Okay, so in the different cases, what appears on the right-hand side is slightly different in the 3 cases. You get an equation something like this. Okay, and then you use these killing spinors in the supersymmetry transformations. Okay, so that's the rough idea. So you can complete what I've said here to supersymmetric Lagrangians, supersymmetry transformations such that these define supersymmetric theories. All right. So yeah, the comment is this looks a bit ad hoc, and indeed it is in the literature, but you can try to be a bit more systematic, and there are a few papers on that so far. In particular, there was a paper by Festuccia and Seiberg last summer. Again, Daniel mentioned this in his talk. So you can have a sort of slightly more systematic point of view by starting with supergravity. You start with supergravity. So it would be in 3 dimensions in this case. And you take a limit of that in which you decouple gravity. You take an m Planck goes to infinity limit to decouple the gravity. And you're left with a rigid supersymmetric theory on a curved manifold. That's the basic idea, which these are examples of. And in particular, the Gravitino equation in supergravity, that implies this killing spinor equation here. So if you're at all familiar with supergravity, you'll know that this sort of killing spinor equation typically comes from setting the Gravitini variations to 0. And that's the idea of this construction by Festuccia and Seiberg. So it's the remnant of the Gravitini equation gives you this killing spinor equation. Okay, and actually just a paper last week by Zampleben and Simpis, I should mention. Zampleben, Simpis. They did this in 4 dimensions, 4D supergravity. Okay, I haven't read all of their papers. They have some kind of classification of these rigid supersymmetric in 4 dimensions, not in 3. Okay, well, I'll mention that. Okay. Perhaps I'll start up here. Okay, so yeah, these examples I'm mentioning are a bit ad hoc, but of course you would hope to be able to do something rather more systematic, and indeed, there are some papers that are starting to do that. Okay, very good. So, yes.
Does this Festuccia-Seiberg technique tell you what the background gauge field has to be?
Yeah, so, yeah, I mean, for example, this killing spinor equation has some integrability condition, which is an Einstein-like equation.
Yeah.
So this will satisfy some components of some equations of motion in the 4-dimensional. So this way you can't choose any gauge field you like here. In this construction, there would be at least some remnant of some equations of motion satisfied. Yeah. Yeah, or if you were sort of a bit more hands-on and naive, if you just tried to do this with a different choice of gauge field, you would find it doesn't work.
So it's the right gauge field to support the geometry.
Exactly, yeah. So this is definitely a more systematic point of view because you've started with supergravity equations, and it sort of guarantees this to work, to give you a rigid supersymmetric field. Okay.
In 3 dimensions, is there a classification of all possible?
No.
So these are just 3 examples.
Indeed, there are 3 examples, yeah. And as far as I know, they're the only example. Well, there's S1 times S2, for which there's a supersymmetric index. You can also take quotients of these, lens spaces, that's other examples. But locally, I think, this is it, if you rule out S1 times S2 as well. All right, that was supposed to be section 1, so this is section 2, localization. Okay, so I probably don't need to say too much about this. We've had quite a lot of talks already. It works the same way as it does for round spheres. I mean, exactly the same. Okay, but I should say something. All right, so localization. So the point is that in these theories, if you look at the expectation value of the BPS operator, so this is the path integral where I insert some BPS operator. This is exactly equal to its semi-classical approximation. Okay, so you see what I mean by that when I write some more down. And in particular, you can compute various quantities, BPS quantities in these theories exactly. And I mean, that's why there's been quite a bit of interest in them. In particular, if I look at 1, that's the partition function. And in fact, that's all that I'm going to talk about. Partition function Z. Okay, but people have looked at Wilson loops and other things as well. You could do that. Okay, so again, I'll just give the idea. And basically, this localization is a sort of fixed point theorem. Fixed point theorem. At least that's how I prefer to think about it, rather than adding these terms to the Lagrangian and all of that stuff. It's kind of exactly like the Dostermayer-Heckman theorem. If you're familiar with that, it's exactly like that. So this is a localization theorem in symplectic geometry, but it takes exactly the same form as this. It says that the partition function is exactly equal to semi-classical approximation. These guys did this in symplectic geometry in the early 80s. It's just in field theory, we have an infinite dimensional version of that. Infinite dimensional setting, because we're talking about a path integral over an infinite dimensional field space. And the symmetry is a supersymmetry. Okay? But apart from those formal differences, it's a fixed point theorem for supersymmetry. Okay, so there's sort of a quick formal argument you can give for this. You know, without starting to give details about adding positive semi-definite terms to the action with some t and taking t to infinity or whatever. There's sort of a dirty quick way of getting it via this fixed point viewpoint. So if I've got some quantum field theory with a symmetry group G, okay, acting on the space of fields, and I have a G invariant operator O, and moreover the group acts freely, then when I look at the expectation value of O, this thing up here, well, that's an integral over the path integral over all of the fields, e to the minus action times O. I'm in Euclidean signature, so it's not IS, it's e to the minus Euclidean action times O. Well, you can just factor out the group action. So you pick up just the volume of the group, you pick up the field space modulo the group action, and you just get exactly the same integrand. Okay, but if G is fermionic, so that means it's generated by a supercharge, Q, then formally this volume is 0. Then the volume of G is 0, since if you introduce some collective coordinate theta along the one parameter group generated by this supercharge, well, because it's a Grassmann variable, the integral of 1 d theta is equal to 0. So formally, this is 0. Okay, so if you have, that goes up there. So in this case, if you have a supercharge acting for which field configurations are well, there are no fixed points of that, then this would be 0, this integral. And this is exactly what happens in this finite dimensional setting as well. This is a symplectic geometry setting. So what that means is that the contributions come from the fixed points. Contributions come from the fixed points. Okay, so if there are fixed points, this field space modulo the group is singular. And then there'll be some contribution potentially from the singularities. So if you have fixed points, you cut out a little tubular neighborhood around the fixed points, and then you see what happens in that neighborhood. The contribution will entirely be from that infinitesimal neighborhood around the fixed points. And here this means Q invariant configurations. Okay, or supersymmetric ones. Okay, so if you apply that to the case at hand, so you have some BPS operator, so it's invariant under Q, just like in the situation here. This will end up being some integral over Q invariant fields, supersymmetric ones, of e to the minus s, O. But then there's also a contribution from the normal bundle to the fixed point set, is what you would say in the usual finite dimensional geometry setting, and that gives you a one loop determinant. Around each background. Okay, that's a sort of quick view of localization. And what's particularly nice about three-dimensional supersymmetric gauge theories is that this integral over supersymmetric configurations reduces to a matrix integral, and that's what makes 3 dimensions particularly tractable. So we heard about 5 dimensions last week, for example, where I also had to include some moduli space of instantons. That does not happen in 3 dimensions, and that's what makes this much more tractable. So e.g., for a d equals 3, n equals 2, un gauge theory, the right-hand side is equal to a matrix integral. Okay, so what happens is that, you get some version of the Bogomolny equations to solve, and the only solutions to that on these compact manifolds are basically trivial solutions. And that's the difference compared to what happens in other dimensions. So the Q invariant fields implies actually that all fields are just 0, except for this scalar sigma in the n equals 2 vector multiplet. That's a constant. If I do this for a UN gauge theory, this is a constant n by n Hermitian matrix. Okay, so in the adjoint of UN, n by n, Hermitian matrix. So the integral over there is an integral over Hermitian matrices. That's a matrix model. Okay, very good. So let me give you an example of what that looks like. So you take this formalism, you go ahead and you apply it to one of these examples. You have some one loop determinant to do, but it's quite doable. And you get the following. So let me take case A2. Okay, they've disappeared. Case A was this Berger sphere. 2 was one particular choice of gauge field. I'll take this with a UN gauge group, and with the Chern-Simons level K. Probably I should probably say what the Chern-Simons action is, right? So it's K over 4 pi, and then you write the Chern-Simons action in 3 dimensions, right? If you trace of A wedge dA plus 2/3 A cubed. Well, plus supersymmetric completion. That's the Chern-Simons action in 3 dimensions. K is the Chern-Simons coupling constant. Okay, so that's K. Okay, then you get some partition function Z. It's going to depend on the squashing parameter, V. I mean, it also depends on N and K. Well, plus also what matter you decide to pick exactly. But anyway, it's a function of those things. And this ends up being, well, it's a matrix integral. So I equals 1 up to n, d lambda I. These are the eigenvalues of sigma. Okay, it's n by n Hermitian matrix. It's got n real eigenvalues. I've called them lambda I. In the formula up there, okay, O is equal to 1, but I have e to the minus action evaluated on the saddle point, and you get a contribution from that. I pi k over squashing parameter v squared, and then sum I is 1 up to n of lambda I squared. Okay, and this comes from the classical Chern-Simons action. Actually, it's precisely the terms I didn't write here. It's the supersymmetric terms involving sigma that contribute to this. This is basically trace of sigma squared sitting inside here. Okay, times, okay, I have to go over to the other board. And then you have a one loop determinant. So I have to do this one loop determinant. This is where it gets ugly. So product over I not equal to j. SB, I'll say what it is when I'm done. Some function, 1 over v, and I have lambda I minus lambda j minus I. Oh yeah. Oh yeah, this is not good. So I is an index on lambda, and that I is the square root of minus 1. Yeah, I'll be a mathematician and write square root minus 1. Okay, and then here I have a product. Okay, and this comes from, this is one loop in the, for the vector multiplet. It's not too bad, these computations, because it's a supersymmetric theory. There's a lot of cancellation between bosons and fermions. So it's not as bad as you might think, these computations. And over here I have a product over chiral matter fields, and I'm just going to write the fundamental representation just as an example. So these will be in the fundamental of UN. You can do any representation you like, just for concreteness. So there's a product over all I is 1 up to n. SB is the same function, 1 is v, lambda I minus square root minus 1. Is 1 minus delta. Okay, and delta here is the R charge of the field. Okay, and then this is one loop for the matter. Okay, so it's a bit complicated, but just for concreteness, just to show you get something completely explicit out of all this.
This is evaluated at b equal 1, because b was not a parameter in this case.
Yeah, I'm about to say what is b, yeah. I've not told you what SB is or b. I'm about to tell you that. So b is 1 over v, 1 plus I square root v squared minus 1. Okay, so that relates b to v. For the one where there was a b squashing, you get something very similar where B is equal to B. Okay, so that's B in the case with the squashing V. And S...
In that case, what is V?
Whatever you want. Yeah, I'm not sure.
No, in that case, V has to be a function of B, right?
Yeah, well, what do you mean by V? V was just some choice of... V was the V I wrote in the metric and gauge field.
In this case.
In this case, yeah.
In the second, you said in the other case.
In the other case, there was a B in the metric.
And there's no V, right?
There's no V, no.
So, but then the formula you said.
The formula here is in terms of B in the other case. So they all look rather similar in terms of, you can write them all in terms of this SB function. And SB has a name, in fact, it's called the quantum dilogarithm. Dilogarithm. Function, so you know, it's some particular special function. It arises in mathematical physics in different areas. It arises in 2D conformal field theory, for example. And actually that was part of the motivation for looking at squashed spheres in the first place, was the relation to 2D CFT via the AGT correspondence. I've told you everything, right? Yeah. Good. Okay, so you get some big matrix model that you have to do. Yeah.
I have a question about the way you present localization. Is this really equivalent to the way other people do, adding a term to the action?
Yeah.
Because I mean, there the one loop determinant would be around the background, which is the term, which depends on the modified action, and so here you had no reference to that. So I mean, if you choose different localization terms in the action, the other point would look different. So the answer would look different. I mean, eventually it will be independent. So.
Eventually, it should be independent of the choices, I would say. Yeah, yeah. It's a bit of a formal argument. This. I think the other one is less formal. It's more clear. It's a bit of a dirty, quick argument, but I think morally it's true.
But so your S would be the full action.
Yeah, the S is the full action and everything. Yeah, yeah. In practice, when you do this, you do it as people have done it in the literature. I'm just trying to give some qualitative argument for why it works, and I think this is correct.
For instance, how much freedom there is in the choice of Q? Because you say that, okay, for Q, the localizing locus is all fields equal to 0. Is this for a very special Q, or is...
Yeah, well, for these series, there's only one choice of, I mean, there's a Q, which is the delta in the supersymmetry transformations, right? Q is the delta in the supersymmetry transformations that you write down, and you use that one. I'm not quite sure what else to say. You don't have a choice. I mean, you construct these supersymmetric theories. The delta is the supersymmetry transformation, and that's what Q is. It's the supersymmetry transformation. Yeah. Okay. Okay. Good. So section 3. So you get some matrix model. It's exact. So very briefly, so I want to get to gravity joules, and for that I'm going to need to go to some large n limit, large n. So we consider some field theory with a large n gravity joule to do this process. Now there are lots of choices for these days. So as Daniel Jaffris mentioned, there are lots of examples with Sasaki-Einstein joules, which I've worked on quite a bit. But for simplicity in this talk, I'm just going to use the ABJM theory. It's simpler. So I'm going to just look at it's an n equals 6 supersymmetric Chern-Simons gauge theory in 3 dimensions. It's called the ABJM theory. It's a UN times UN with Chern-Simons couplings K and minus K for the 2 factors of UN. Chern-Simons matter theory. n equals 6 is almost fully supersymmetric in 3 dimensions. N equals 8 is maximally supersymmetric. And the matter, well, okay, there's some bifundamental matter that you can draw with a quiver diagram. Okay, so if you draw the 2 UN gauge groups like this, you have 2 in the bifundamental going from that to that, and then you have 2 in the conjugate representation. And this is dual to, well, if you put it on S3, it's dual to M theory on ADS4 times S7 mod ZK in the n goes to infinity limit with k fixed. Okay. So, you can take this result for this matrix model here, and you can just plug in this particular theory. So it's got 2 copies of UN, so I'll have 2 sets of eigenvalues, say lambda and lambda tilde for the 2 gauge groups. I've written the fundamental representation answer here. The bifundamental is just some small modification of that. And I'll get some partition function, which depends on the squashing V in this particular case, and on, I grabbed it off, n and k, that's up there. And I want to take the n goes to infinity limit with k fixed. Okay, so there's a long story about how you actually do that. I'm going to completely suppress it and just tell you the answer. So minus log z is equal to, and then I'm going to have my various cases. So it's A1, 2, and case B. Okay, so case A was the Berger sphere. 1 and 2 were 2 different gauge fields. Case B was the elliptically squashed sphere. And there's some universal n to the 3 halves, k to the 1 half, square root 2 pi over 3 factor, which is common to all of them. This is the answer on the round sphere. Okay, and here I have 1. Okay, so the answer in this case does not depend on the squashing. And this was why Imamura and Yokoyama came along in September and tried to consider another example. So in fact, for the first choice of gauge field, the partition function doesn't depend on the squashing at all. So in that sense, it's not interesting. You can explain that in terms of representation theory. So the killing spinner lives in different representations of the symmetry group in the 2 examples, in fact. So there's an SU2 isometry of the metric. In the first example, the killing spinner is a singlet under SU2, and in the second example, it's a doublet. And we'll see this in the gravity dual shortly. Because of this structure under the group, you can see that the non-trivial dependence on the squashing entirely comes from this one loop. And when the killing spinner is a singlet under SU2, you can see that all the interesting dependence on the squashing just cancels between bosons and fermions. Okay, and that's why they describe this as the not interesting case. Okay, anyway, so I get 1. In the second case, you do get a dependence on the squashing, and it's just 1 over v squared. And this case is b plus 1 over b squared over 4. Oh, yeah, and I think interesting, if you use the formula for b in terms of v here, this is the same. So this is also b plus 1 over b squared over 4. If I use the formula for b up there it is, up there. I think that's the same thing. Okay, good. So this is the large n limit, and obviously the interesting question now, in the last 15 minutes, is can I understand how to compute this in a supergravity dual? And, well, you can. Okay, so 4 is the gravity dual. Okay. So I'm going to work in a supergravity theory in 4 dimensions. So, yeah. So I use G equals 4, N equals 2, gauge supergravity. Okay, it's not obvious that that's the right thing to look at the moment, because the gravity dual is really an 11-dimensional thing. But I'm starting with a 4-dimensional supergravity. As you'll see in a moment, that is the right thing to do. So what is this supergravity theory in 4 dimensions? Actually, it's just Einstein-Maxwell theory. Okay, so the Einstein-Hilbert action is 1 over 16 pi g Newton g4 in 4 dimensions, square root. Well, okay, normally you would write minus g. I'm going to be in Euclidean signature, so it's actually square root g d4x. I have the Ricci scalar. I have a cosmological constant, which is normalized to 3, minus 3. This is cosmological constant. And there's a gauge field. And that's the usual Maxwell axiom for U1 gauge field. Okay, so that is just Einstein-Maxwell theory, in fact. And so Einstein-Maxwell theory can be made supersymmetric in 4 dimensions, and that's, you get this gauged supergravity. And it's a fact due to gauntlet. Okay, following the conventions in workshop, I will omit the rest of the collaborators of Jerome Gauntlet, because I can't remember who they are. So Gauntlet et al. Tells us that any supersymmetric solution to this 4D theory uplifts to a supersymmetric solution in 11D. Where do I need to go? Here. Okay, so another way of saying that is that there's a consistent truncation of 11-dimensional supergravity to this 4-dimensional gauge supergravity theory, which keeps just the metric and a U1 gauge field. And because of that, any supersymmetric solution I have here uplifts to an 11-dimensional solution. So for example, ADS4 is obviously a solution to this theory, maximally supersymmetric, and this will uplift to ADS4 times S7 via this uplift. Okay, but if I had a different solution, I would be able to uplift it to some 11D solution where the S7 is fibered over the 4-dimensional solution, and there's some fibration structure with this U1 gauge field. I'm not going to write out. You can maybe imagine what it looks like. There's some uplifting formula. I'm not going to write it. Okay, so this is the problem I have. Okay, so the boundary of that is some squashed sphere. It's a conformal boundary, really. Conformal, squashed, S3. And I also have some fixed gauge field on there, which I call A3. And I want to find some 4-dimensional filling of that. So it's really like a Dirichlet problem. Where I have some fixed data at infinity, conformal data, and I want to find a supersymmetric supergravity solution that fills that conformal boundary with the choice of gauge field. So I need to find a supersymmetric supergravity solution with this boundary data. And I even want a bit more than that. I would like my 4-dimensional supergravity has a killing spinner, when I restrict that killing spinner to the conformal boundary, I want to recover the spinner that these guys used, satisfying the same killing spinner equation on the boundary. Okay, so the 4D killing spinner restricted to the boundary should equal the 3D killing spinner. Okay, and I should recover the 3D killing spinner equation that they used from the 4-dimensional one restricted to the boundary. Okay, so if you can do all of that, that's going to be the gravity dual, right? Okay, now if you give me a general boundary, I wouldn't know how to solve that problem. But these particular boundaries are quite nice, and if you happen to know a bit about supergravity literature, you can guess what you should do. And in practice, that's what we did. Okay, so I'll explain what happens in the 3 cases. So case A is the Berger squash sphere. M4, this 4-dimensional filling, so I'll give that a name, M4 inside here. M4 is Taub-Nut, ADS. This is a very old solution, known for a long time. You must go back to at least the 70s as a solution to the Einstein equations. So it's an Einstein metric on R4. Okay, R4 has boundary S3, so it's a squash boundary. And a gauge field A in supergravity is an instanton. So it's a self-dual U1 gauge field. It's worth writing the metric, I think. So it's the S squared of Taub-Nut, just so you can see that there's some honest computation going on. Okay, so you see the squashing parameter V is coming in here. Omega of R over V squared, R squared minus 1 over 2 V squared. And I have this hop fiber. Okay, so the metric looks something like that. Omega of R is a radial function. Okay, so R is the radius. Omega of R is R minus 1 over 2V all squared. And then it's 1 plus R minus 1 over 2V. 1 plus 3 over 2V. R plus 3 over 2V. This is some quartic in R. Okay, so that's the metric. It's an Einstein metric on R4, negative curvature. And if you look as R goes to infinity, you get boundary the squash sphere that I started with. Okay. Now that by itself is not supersymmetric, but if you add an appropriate gauge field, it is. And there are 2 choices. Okay. So case 1 is, well, you have to pick conventions what you mean by self-dual and anti-self-dual. But in some convention, there's a self-dual instanton, A. And it's a quarter BPS solution to this theory. And the other one is, in the same conventions, anti-self-dual instanton. So they're different. I mean, different gauge field. And this one's actually half BPS. And you see in the solutions this behavior under the SU2 isometry. Here it's a singlet. That's why it's quarter BPS. This one's a doublet under SU2, so you have 2 of them. That's why it's half BPS, whereas this one's a quarter. And this precisely works, okay? So these are supergravity solutions. You can work out the gory details of the killing spinner, restrict it to the boundary. You get precisely the killing spinner and the killing spinner equation that was in these field theory papers. Okay, so that's good. So these are obviously the right gravity duals. Then you can compute the partition function in gravity. Okay, so minus log z gravity. In the Euclidean quantum gravity limit, semi-classical limit of quantum gravity, so minus log z will be S Einstein-Hilbert, the Einstein-Hilbert action. You have to, so these are things with boundaries. So there's a Gibbons-Hawking boundary term. And as you probably know, that's not finite by itself. There are some boundary counterterms that you add. So there's S counterterm, which are the unique counterterms that you can add to make this finite. And you take all of that and you evaluate it on the solution. Okay, so I've just told you a supergravity solution. There's the metric. Okay, I didn't write down the instanton, but I could do. And you take all of that, you plug it back into the Einstein-Hilbert action. There's a Gibbons-Hawking term to compute. There's some counter terms to compute. And if we use that 1 over 16 pi g4, so this is some universal factor, n to the 3 halves, k to the 1 half, 1 over, I think it's 3 pi root 32 or something. So if you plug this in, this comes just from the usual Kluser-Klein reduction on the 7 sphere in this case. So the volume of the 7 sphere is hidden inside this formula. Get precisely the large N field theory result. So this is actually a miracle when you see it happen. Okay, so there's non-trivial dependence on this squashing parameter when you do this computation. Okay, so for example, this Einstein-Hilbert term, as I remember, it depends on the squashing parameter, its square, its cube, and its 4th power. And similarly here. And when you put them all together, in this case, you just get 1 at the end of it. And in this case, you just get 1 over v squared. Okay, so there's some miraculous cancellations here. It's quite a complicated solution, but you precisely recover the field theory results, which were very simple. Okay, so it's really miraculous to see this come out. It doesn't look like it's going to work when you first start, but it does. And okay, the case B is similar. So the case B, you can actually fill with ADS4 in an elliptical slicing. And again, A, the gauge field A is again some instanton. Okay, so this case 4 I've cheated slightly. So the case in the literature, the metric I started with is actually a little bit different than the one in the literature. The elliptical S3 metric in Hammer, Hosamichi, and Lee was obtained by some isometric embedding in R4. The metric that I wrote is actually slightly different. It's isometrically embedded in ADS. So we kind of cheated in that sense. We don't know actually a gravity dual to the one that's embedded in R4. Don't know if it exists or not. But the point is that the metric that I chose, the localization goes through in the same way. You get a function of the squashing B with this SB that I just erased, and it matches. Of course, because of this, because I fill it with ADS, actually the metric I wrote to begin with is conformally the S3 metric. So it's a bit of a cheat, but it has a non-trivial gauge field turned on. This answers your question. So this is an example of something that's conformal to S3, so it's S3, with a non-trivial gauge field turned on, which is supersymmetric, and it's 1/4 BPS, this one again. Okay, I'll stop there.
distinguishes self-dual and anti-self-dual from the fault perspective? What fixes the orientation?
Well, well, you can pick whichever orientation you want. I mean, it's not Caleb, but if you fix a frame, E1, 2, 3, 4, then in one it's self-dual, in the other it's anti-self-dual. I mean, what you call self-dual and anti-self-dual is up to you. If you reverse the orientation, you'll see. Well, no, this one is.
You also change the
No.
factors and change the function.
No, I mean they're not the same. They're not the same gauge field, right? This one is a completely different gauge field than that one. Yeah, otherwise you're right. It wouldn't make sense what I just said. They're not the same. I mean, they can't be the same because they give a different answer for the action.
Yeah, that happens to be self-dual.
Yeah.
You could call them both self-dual.
You could call them both self-dual. Yeah, exactly. But yeah, they're different. I mean, I should call this A1 and A2. I mean, even at infinity, they're different, right? The two gauge fields were different. Yeah.
Any more questions?
The limit of V very large, extreme squashing, the behavior of the partition functions in case 1 and 2 is completely different.
Is it the same metric? Sorry, do you mean case A and B?
A and B, yes.
Oh yeah, A and B. Yeah.
1 and 2 on the board there.
Oh no, this was case A. Case B with some other squashing, right? Case 1 and 2 have the same metric.
Okay, but one of your partition functions had a 1 over V squared.
Oh right, yeah,
And the
that's
other
true.
one didn't.
That's true, yeah, that's right.
Is there some intuitive way to see why they should have such different behaviors if you took V very large?
I don't know.
So in one case, I mean, it looks like the theory's freezing or something.
Yeah, I mean, I'm not sure. I mean, if you put V equals infinity, it's a singular metric.
Yeah.
So the V goes to infinity limit is some singular thing. I mean, the circle fiber collapses to 0. So in some sense, you get just an S2.
Yeah.
I'm not sure. I didn't think about that. Yeah. I mean, at some technical level, it's easy to understand why one depends and the other doesn't. At some group theory level, you can see that. Otherwise, I'm not sure.
No questions? If not, I have a question.
Yeah.
If I can just, one class of 3 manifolds, you obviously consider only squashed 3 spheres here.
Yeah.
But one class that might be somehow related is S2 cross S1, just the factorized manifold. Of course, that's physically very important. Is there any chance that can arise as a limit of some squashing which decouples the hop fiber from the base, and so you get S1, the S1 cross S2?
Yeah, yeah, sort of. Yes, I mean you can. Yeah, you can do that. You have to also scale the period of this coordinate psi at the same time. So it's not a limit of the solutions I've described here, but it is a limit of the supergravity solutions in some sense. Yeah.
But in this way, you think you'd be able to recover the S2 cross S1 partition?
Well,
part?
not directly from this, no. So the limit where the squashing goes to infinity is just singular. But if you also rescaled, if I also rescaled psi by the inverse factor, then the cos theta term will get scaled out, and you would end up with S2 times S1. So there might be some way of doing it, but you would have to take a different period for psi, and also send that to.
Couldn't you then plug it into this formula, in that limit?
Maybe. Yeah, you might be able to do something like that. I'm not sure.
More questions? Okay, let's thank James again.